Okay, could you do a sound check? Great, thanks very much. All right, in today's lecture, I'm going to finish up the discussion of cosmic expansion began last time by introducing one of the key thermodynamic tools for analyzing the cosmic expansion history, that is energy conservation during an adiabatic expansion phase. And then I will show you how to solve the Friedmann equation for a few important cosmological models, and then we will talk about the actual thermodynamics and some of the key events in the thermal history of the universe. So we're going to consider a co-moving volume as before. Co-moving volumes are important because if particle number is conserved in such volumes, then we have a fixed number of particles, and so we just have to keep track of the energy density and pressure through the statistics of those particles. Local energy conservation in this volume says with adiabatic expansion there's no heat exchange with the surroundings, so we just have that the energy in that volume, which I'm using rho to be both the energy density and for a non-relativistic gas the rest mass density, but in general it's the energy density, plus the pressure times the change in the volume is 0. Now we're going to consider several cases for different relations between P and rho, equations of state. First, two common cases, and then we will generalize. And I will usually take units where C equals 1. So when the pressure is much less than the energy density, this happens, for example, when the temperature is much less than the mass and applies to non-relativistic matter. Then we can drop P compared with rho, and we have that rho is proportional to a to the minus 3, just reflecting the volume dilution of particle number. The second common case is a relativistic gas where the temperature is much greater than the rest mass, for example, for photons or relativistic neutrinos. Cosmologists, in keeping with their traditions of coming up with funky names, call this radiation. And of course, in such a case, this equation can just be written as 0 equals the differential of rho a to the 4th over a, which implies that rho decreases faster with expansion. And that is because rho is for conserved particle number, the number density of particles times the energy per particle. Remember that for photons, the energy redshifts, it decreases in proportion with 1 over a times 1 over a cubed number dilution. That gives you a to the minus 4. I will now generalize for the case of a so-called W fluid, where W is any constant. This is often used as a model equation of state, and we can see here two limiting cases where it does apply. Another case, of course, is the cosmological constant, where W is minus 1. Then we get 0 is equal to differential of rho a to the power 3 times 1 plus W divided by a to the 3W implies that rho is proportional a to the power minus 3, 1 plus W. And you can check that for the two previous cases. Also, you see that if W equals minus 1, for vacuum energy or cosmological constant, indeed rho is a constant. So for a vacuum energy or cosmological constant. This is a constant. And as a little exercise, you can show that if omega lambda is 0.73 today, this rho vacuum is 0.002 electron volts to the fourth power when you choose units such that C equals H bar equals 1. I have a few other little homework problems that I can suggest which follow from the Friedmann equation and from this simple thermodynamic rules. The first is combine the Friedmann equation, which is A dot squared plus K is 8 pi over 3 G rho A squared, together with these energy conservation laws. Actually, the top one, underlined, is the most general, to show that A double dot over A is minus 4 pi over 3 G times rho plus 3P. A very important relation, and one that shows, for example, that the universe should decelerate with a negative A double dot unless the pressure is negative, assuming that the density is positive as it should be for all well-defined mass energy. And for a cosmological constant, P is minus rho, so this becomes minus twice the energy density, and that's how we can get cosmic acceleration. That's a very useful result. A second thing you can show, that if A double dot is less than 0 always, let me say, and A dot is greater than 0 always, that is an expanding universe that is always decelerating, then there was a time in the past when A is 0, and it occurred at a time, or measured from then, the current time, T naught, times H naught, to make it dimensionless, is less than 1. So T naught equals T today minus T when A equals 0. So the Hubble time that I defined last time, the inverse of the Hubble constant, is a very useful time scale. It gives an upper bound to the age of the universe if the universe, its inverse gives an upper bound, inverse of H, if the universe was always decelerating. In fact, for the case of an always matter-dominated universe where rho goes as A to the minus 3, the age is 2/3 of the Hubble time. So it's less, significantly less than the Hubble expansion time. And that created a lot of difficulties for cosmology in the last few decades until the Hubble constant was measured to have a lower value than many people thought. Current value estimated at, as I said, 72. There was a time when people were thinking that it could be even higher than that. And with that factor of 2/3, it would mean that the age of the universe inferred from the cosmological models could be less, for example, than the ages of the oldest stars, which were measured in old star clusters as being in excess of 10 billion years. This has finally been resolved in this decade, the last decade, with the accurate measures of the Hubble constant and the realization that cosmic acceleration means that you can have an age of the universe that is comparable to or even larger than the Hubble time. So those are very useful results. And a third useful exercise is to integrate the Friedmann equation to get T of A. that's the expression that you'll find promptly from substituting a sum of these W fluids, each with a parameter W sub x. So you can put in 0 for matter, 1/3 for radiation, and so forth. And then this omega k is the curvature piece that I mentioned last time. And what you should do is to solve this for several cases. They're very easy to do. One would be 0 curvature and a single W fluid. So we would call that a universe which is dominated by a particular kind of mass energy density. For example, a matter-dominated universe, or a radiation-dominated universe, or a lambda-dominated universe. Another case that's quite useful is, again, omega k equals 0, but with matter plus radiation. Here, when I say matter, this is again the astronomers' or cosmologists' shorthand for non-relativistic matter. Radiation means relativistic matter. So this would be a universe consisting of dark matter and baryons, atoms, plus photons and, let's say, relativistic neutrinos in the period when the neutrinos were relativistic, somewhat before the present time, but not so early that the let's say we go back to the quark-hadron transition and the baryons are broken apart into relativistic particles. So there are a series of stages in the universe that we will discuss shortly where transitions occur, but for significant periods of time, these kinds of models are really useful for looking at the cosmic expansion. And then a third case, which can also be done exactly, is when the curvature is not 0, and there's matter only. That's relatively straightforward. If you want a challenge, do the case of curvature plus matter plus radiation. That also can be done exactly, and maybe you'll get Mathematica to do the integrals. I will give you a hint for B and C. It's very helpful to define a new time variable called tau. It's called the conformal time for reasons that I'll make clear in the next lecture. It's kind of like a co-moving time variable. Remember that we had this R0 variable gotten by taking physical distances, dividing them by the A of t expansion factor. This is the same idea. You can think of this tau as a kind of co-moving time variable. It just so happens that you can then get simple expressions for A of tau and t of tau in these two models. So conformal time is computationally nice to deal with. So now we can take the different phases of cosmic evolution and just make a graph of what the, for example, the energy density looks like, and then we could graph the scale factor. I won't dwell on this, but I will here show the main stages of cosmic evolution in terms of log rho versus log A. A equals 1 today, conventionally. And I'm going to have, at early times, we speculate, a period where the universe is exponentially expanding, approximately a de Sitter phase. That's the inflationary era. I'll talk more about that next time. So the end of the inflationary era is called reheating. So this is W minus 1, inflation. Then we have a period when W is 1/3, and the density goes like A to the minus 4. This is where relativistic particles predominate. Radiation dominated for a long time. And then the universe makes a transition to matter domination when the energy density in the cosmic microwave background and the neutrinos becomes less than that of the atoms, baryons, because of the redshifting of the energies of relativistic particles. That occurs at a time called equality, matter-radiation equality. And after that we have matter domination. Where W is effectively 0. Of course, it's not exactly 0, but it's much less than 10 to the minus 6 today. And then we have a transition towards what looks like a lambda-dominated universe today. And I put that in question marks because that's our current best model. But I would say it's not as convincingly demonstrated as, for example, the fact that we had a radiation-dominated era earlier on. We obviously measure the photons. We know how they redshift. We know the universe was radiation-dominated early on. We know very well the physics through this intermediate period, largely from the CMB combined with structure formation. It's the new physics that we were seeking at the extremes of our cosmic expansion history, the beginnings and the ends. Actually, I want to put up one more little problem for you, which relates to this question of whether the universe is, in fact, lambda-dominated. So for a fourth homework problem, show that if W is less than minus 1, then A actually goes to infinity at a finite t. And that's a physical singularity. Just like when A goes to 0 for models that are decelerating, then that's also a physical singularity, curvature singularity in general relativity. And this one is called the Big Rip. And Rob, are you here, Rob Caldwell? Okay. He may be the one who gave the model that name. Anyway, he's written papers about the Big Rip, so you can ask Rob about that. All right, so this is the end of the presentation about cosmic expansion in general. Before I turn to thermodynamics and the thermal history, it's a good chance for me to stop and take any questions. All right, we'll continue then. I'll find the eraser.
I think that swamp is better to write before rather than the yellow fluff there on the table.
I guess this may be a little faster. Thanks. All right. I want to start with two key concepts. Kinetic equilibrium, which is often simply called thermal equilibrium. And kinetic equilibrium arises when elastic scattering exchanges particle momenta faster than the Hubble expansion rate. Basically, kinetic, yes?
Can I go back a little bit to your fourth question?
Oh, sure.
When you talk about curvature
Yes.
Does that deal with black holes?
A very good question. Are the curvature singularities that I mentioned, this is jumping back to the homework exercise where I mentioned the Big Rip and the Big Bang, how are those related, if at all, to black holes? They are different. The geometric structure of the singularities is different from those of a black hole, but they share the common feature with the black hole that the Riemann curvature is divergent, it blows up. What that means physically is that the gravitational tide over an extended body becomes infinite. In the case of a black hole, this is often colorfully described as the spaghettification that happens to someone falling into the singularity of a black hole. In that case, the tide is such that the gravitational force pulling on your head and your feet is very different, and so you are, if you fall in feet first, you're going to be pulled into a very thin ribbon, and actually there's also a compression in the free fall frame due to gravity, which compresses you, so you get extended into a strand of spaghetti. In the case of the Big Bang and the Big Rip singularities, the geometric structure is a little bit different. These are not localized spatially in the same way, but there are components of the Riemann tensor that diverge, which would make the continuation of the space-time, using general relativity at least, impossible.
So you're saying it's like a bare singularity, or like can you like form some kind of like horizon around it? Or
They're not spatially localized, so the concept of horizon, event horizon, does not show up for these types of singularities. And you don't have problems with information flowing out of the singularity because these singularities are one way in time. Okay. Of course, no one believes that general relativity should be pushed to singularities and beyond. We think that general relativity will have to be replaced. For one thing, quantum gravity arguments tell us that that's the case. I could say, as a corollary to this proof that when the universe is always decelerating, there was a Big Bang, you can show that, for example, if the universe is always accelerating, there wasn't a Big Bang. So you can look, for example, at the de Sitter universe and see that the Big Bang singularity disappears. Now, there are very interesting questions about the geometric structure of de Sitter phase and what could have preceded it if the universe did start out in a de Sitter phase. I'm not going to get into that, but Leonardo Sanatori or others might when they talk about inflation in the early universe and multiverse models. Okay, are there other questions on the first part before I launch back into equilibrium? Okay, there will always be time for questions during the breaks and meals. So kinetic or thermal equilibrium occurs when elastic scattering allows particles to exchange momenta and therefore for their momentum distributions to relax to a thermal distribution specified by a temperature and a chemical potential. Now, we can calculate, of course, the rates of elastic scattering for any particle species with itself or with other particles so that this exchange of momentum and energy is possible. But you have to ask fast compared to what? And the Hubble timescale is the relevant one in the cosmology because, remember, the energies of the photons measured by co-moving observers are decreasing by the Hubble expansion. And so the question is, can interactions of photons with other particles maintain kinetic equilibrium? That's why you want to compare with the Hubble time. And the same is true not only for photons, but for other particle species as well. And then the second key concept is chemical equilibrium, where instead of elastic scattering, we look at processes that create or destroy a given particle species are faster than the Hubble expansion rate. Typical example of this is electron-positron pair annihilation that occurs in the early universe. When the temperature is much higher than the electron mass, then particle interactions will not only exchange momenta, but they can create pairs, create E plus E minus pairs. When the particle energies are not large enough to create pairs, the pairs will annihilate. And for a while, the abundances of those particles will be given by thermal distribution functions. But now, the mu is not arbitrary. The temperature is still given by the temperature of the heat bath that the particles are elastically scattering with, because typically the particles have elastic scattering remaining even after they fall out of chemical equilibrium. But what's important for chemical equilibrium are the chemical reactions themselves, which set the particle numbers and therefore the chemical potentials. So if I have, for example, binary collisions, A plus B goes to C plus D, then I have, in chemical equilibrium, this relation between the chemical potentials. And I can never remember what it's called. You may help me. It might be called the law of mass action. I don't remember it. But this is a chemical equilibrium condition. And there's a very important example of that process, which is Bremsstrahlung. So, for example, electromagnetic Bremsstrahlung. In the early universe, I have electrons and protons, well, protons after quark confinement. This can go to E plus P plus photon, both the forward and the inverse process. When those are in equilibrium, that implies that the chemical potential of the photons is zero. Okay? But when this process is not in equilibrium, there may be processes that could change the photon number, and then, then it would develop a chemical potential. Okay? So one has to look at the scattering processes to calculate these things. Yes? That's a wonderful question. What is the chemical potential for the neutrino? We don't know, actually. That depends on neutrino interactions in the early universe. And I may say a little bit about that as we go, but in the standard model, well, in the standard model, neutrinos don't have mass, but in the simplest extensions, the chemical potential is zero. But there are models that can produce a neutrino chemical potential. So that's quite important. We'll talk about that a very little bit later on. Yes?
Sorry, what's the main chemical potential of photons different materials? Is that related with photon mass?
No. No. Chemical potential different from zero for photons, of course, is not a Planck black body, but it can be generated, as you know, if you take a Planck black body and thermally couple it to another particle species, which does not exchange particle number. It doesn't create or destroy photons, but can cool or heat the photons. When you cool photons at a fixed number, you can actually produce Bose condensation of photons. And that has actually been physically realized in laboratories on the Earth in the last few years using microwave cavities. If you heat the photons but conserve particle number, which can be done by Compton scattering, then you produce what's sometimes called a Comptonized black body spectrum, characterized by the temperature and chemical potential. There was a period of time when people thought that the cosmic microwave background might actually have a non-zero chemical potential through some of these heating processes. There was a rocket experiment in the late 1980s which suggested deviations from the Planck black body law in the so-called Wien tail of the distribution, and those were interpreted as possibly being the existence of a non-zero chemical potential. When the COBE satellite made its measurements starting in 1990, the non-zero chemical potential went away. The limits on the chemical potential now are quite small, less than about 10 to the minus 4 of the temperature. Yes?
So the nuclear distortions of CFD are basically non-zero threshold.
Exactly.
Right?
Exactly.
But the limits of the type distortion is not unlimited, so there is still room for distortion, right?
Very small distortions. Maybe I'm wrong about the 10 to the minus 4. I think I don't. You and I could check on the limits from Kobe-Firas, which probably still has the best limits on the spectrum shape. But the chemical potential is now known to be quite close to zero relative to the temperature. Okay. So I want to consider the case where chemical equilibrium applies, and so I will allow, in principle, for a non-zero chemical potential. So I have a phase space distribution function for species X. F sub x is a function of the momentum, and typically in thermal equilibrium, you can work in a rest frame where the distribution function is isotropic, so the particles don't have any net streaming, Lorentz boost to that frame, and where locally they have no gradients of the density or concentration of the particles. That's the case of perfect thermal equilibrium where you don't have any variations in abundance or concentration. I've been assuming throughout this discussion that we're in a phase of the universe where we can neglect spatial gradients. Of course, this could also depend on time. I'm just going to leave out the time dependence for right now. So given such a distribution, and well, let me write its form in thermal equilibrium. Taking the Boltzmann constant to 1, I've got my two parameters, the chemical potential and the temperature, plus 1 for fermions, minus 1 for bosons. This G is spin degeneracy, the number of spin degrees of freedom. Typically that would be 2s plus 1, but for massless particles like photons, there are no longitudinal photons in vacuum, so for photons, G is 2. And the 2 pi h bar is just Planck's constant cubed. And you all know this formula from elementary stat mech. So this is the mu that people fit when they look for mu distortions of the CMB. And of course, using this distribution function, you can get the number density and the energy density. The number density of particles of species X is the integral over momentum space, d3p, and the energy density, rho sub x, is the integral of the energy for momentum p, which is p squared plus m squared, square root, integral d3p. Any questions here? Okay, I'll talk about black body radiation then next as a special case of this. The photon-photon cross-section is pretty small, especially at energies less than the electron mass. So how can photons achieve thermal equilibrium? They do it by elastic scattering with charged particles, and especially with electrons or with protons, but Since the universe is charge neutral, as far as we know, you're only going to have free electrons if you also have free ions. And the scattering cross-section for electrons is bigger. It's the Compton or Thomson cross-section. So blackbody radiation arises when kinetic equilibrium results from Compton or Thomson scattering. Of photons and electrons. The general process, of course, is Compton scattering. Thomson scattering is the non-relativistic limit. So in the electron rest frame, it means that the photon energy is much less than the electron mass. Now, there's one further important point to note about the CMB. Maybe I should make that point here by giving just the numbers for photons. Let me write down the photon number density for a black body with mu equals 0 and T equals 2.725K. The number of photons is 400 and some per cubic centimeter. Let's see if I have the exact number. That is much higher than the number of electrons or protons in the universe. The photon to baryon ratio is enormous, or the entropy to baryon ratio is enormous, and that is, of course, a reflection of the baryon asymmetry in the universe. Not only are the photons numerous, they have a lot of energy density compared with the thermal energy density of protons and electrons today, of the atoms today. When we say that the universe was matter-dominated, we mean that the total energy density of the matter exceeded that of the radiation. But it includes the rest mass energy. When temperature is much less than mass, it's dominated by the rest mass energy. If you subtract off the rest mass energy density of the atoms and electrons and look at the rest, call that thermal energy, it's much less than the energy density of the CMB, at least since parannihilation. That means that the photons, the CMB background is a huge thermal bath. It's very hard to perturb the temperature of the CMB through any interaction with atoms. That's why when there was a big mu distortion claimed in the late 1980s, it was shocking because you could not produce this from interactions with atoms as we know them. You only produce it by having some exotic process in the early universe. So the CMB is a wonderful heat bath. It's very hard to exchange heat since electron-positron parannihilation. Not just the photons, but the CMB. Of non-relativistic atoms, basically, when you have a gas of atoms or non-relativistic electrons. So that kind of makes the thermal history a lot simpler. It means that the photon energies are going to redshift as 1 over the expansion factor since the early universe with very little perturbation caused by atoms. Now, there are caveats to that. If I have a relativistic gas of electrons sitting around somewhere, like in the vicinity of an accreting black hole, those electrons can Compton scatter the photons to higher energies. Or if I have a hot plasma, but not quite relativistic, in a cluster of galaxies, that plasma, again, can upscatter some of the CMB photons. That's called the Sunyaev-Zeldovich effect. Those are very small effects. They affect a tiny fraction of all the cosmic photons, which are entirely dominated by the CMB. So I'm going to focus on where most of the energy is. That's in the CMB. Now I want to introduce you to some of the astronomical notation for the measurements of CMB radiation intensity. because astronomers don't measure phase-space distribution functions. They use telescopes that have directionality, and they measure certain frequency ranges with certain frequency responses. So I will show you how those are related. Astronomers measure a quantity called specific intensity, sometimes called brightness. And in general, they measure it as a function of, well, frequency or wavelength. It depends on the kind of spectrograph or imaging spectrograph that astronomers use, but typically they describe it using frequency nu, which is appropriate for radio waves. Optical devices typically cannot operate at the frequencies of optical photons, which are in the 10 to the 15th hertz range. We don't have electronics, for example, that works that fast yet anyway. So wavelengths might be more appropriate, and in fact optical spectrographs disperse light with the prism or a diffraction grating according to the wavelength. But for the CMB, the measurements are made with radio or microwaves, where frequency is the observationally right quantity. So I'll use the frequency nu in some direction. And I could describe that with the unit vector, but I won't bother here. And what they will measure, oh, by the way, this intensity is typically using the symbol I sub nu. I for intensity, subscript nu meaning per unit frequency interval. That's where the word specific comes. More astronomical jargon here. Well, what does this mean? Take a little box where I'm going to have some incident electromagnetic radiation coming from a given direction. So I orient my box so that the radiation is normally incident onto some face with area dA. And I'm going to make the size of that box c dt. C here the speed of light, just so you'll understand that this distance is crossed by the light in a time dt. So I have a little volume, and I can ask how much energy of photons is in that volume. So the volume contains energy dE in photons. And taking the dE, the dt, the dA, and so on, I define the black body brightness by taking instead of the symbol I nu, which is the general astronomer's formula for intensity, the intensity of a black body, B nu, which I'll show you as a function of t in a moment. I take the energy divided by the volume. Well, not quite. I divide it by dt times dA times the range of frequencies sampled, bandwidth, times the solid angle. So this formula assumes that my radiation is not coming out at a single frequency, but it is a continuum, a continuous spectrum, such that when I increase the frequency range, I get more energy E for a continuous spectrum. If I have a spectral line, I might represent this intensity with the delta function of frequency centered on the line, or I might put in the correct line profile from atomic theory. Okay. So we're going to work with this intensity, and I'll write down the Planck formula momentarily. But before doing that, I want to point out one thing that I've neglected so far in talking about photons, and that's photon polarization. Well, I mentioned that the photon has 2 spin degrees of freedom, but thinking of the photon as classical electromagnetic waves, if I have a photon propagating in the z direction, then if it's linearly polarized, it could have the electric field in the x direction or in the y direction or at some other angle. And of course, I can have a superposition of incoherent waves or even partially coherent waves. And so, strictly speaking, I should not have a scalar distribution function, but I should have a density matrix. So to describe photon polarization, I'm a little bit out of order here, and I apologize for this. I started out with the phase-based distribution. I introduced intensity, but now I'm going to go back to the phase-based distribution for a moment. So I apologize, this is a bit out of order. I could have done this before. For photon polarization, this F of photons goes to a 2 by 2 Hermitian matrix. And I think I'm going to give you a chance to copy this, and then I'm going to write that matrix on this board and talk about what the photon polarization means, and then return to writing down the temperature dependence of this function and the thermodynamics of blackbody radiation. Okay, are you with me here? So in place of a scalar distribution function f sub gamma, we have a 2 by 2 matrix, and I'll explain the entries here. I'm labeling the rows and columns by directions in what's called the polarization plane. So if I have photons traveling in the z direction, the plane in which the electric field vectors lie is called the polarization plane. If you want to think about a photon wave vector k, the polarization plane is perpendicular to k, so I'm labeling it by its directions x and y. These quantities I, q, u, and v are called Stokes parameters. And they're measured in the following way. A polarizer is a material that will propagate radiation, electromagnetic radiation, and it will extract, for a linear polarizer, the components of the electric field in a given direction. A sheet of Polaroid sunglasses do this. So if my x and y directions are like this. Now the polarization plane is the plane of the blackboard. If I orient my polarizer in the horizontal direction, I will pick out I plus Q over 2 as the measured flux coming through this polarizer, the measured specific intensity. That's from the XX component. If I have a vertical polarizer, I get 1/2 of I minus Q from the YY. If I have a 45-degree, I get 1/2 of I plus U, or in the other orientation, 1/2 of I minus U for linear polarizers. So you see that if I add the intensities coming from crossed linear polarizers, I get I for the total intensity. And I can put a subscript nu on it or not. It doesn't matter. The polarizer is supposed to always pass light of a given orientation irrespective of its frequency for a perfect polarizer. So, okay. Now what about V? V arises when you have circularly polarized light, and you can pass circular polarization with a pair of linear polarizers and what's called a quarter wave plate, something that rotates a phase of the light by 1/4 of an oscillation cycle. I won't sketch that. I'm sure you've all seen it. But the point is that this V is what a particle physicist would normally think about as measuring directly the helicity of the particle. It's been said. So there are a couple of relations about these. One I mentioned is that the sum of intensities through crossed polarizers, it's I plus or minus V over 2 is what you measure with circular polarizers. It is equal to I, total intensity. And there's another relation which says that I squared is greater than or equal to Q squared plus U squared plus V squared. Showing that you have to use a little bit of algebra of the electric field components of the light, or you have to work with the operator algebra for photon number states if you want to deal with photons of a given potential, vector potential. You'll find this in optics books. Okay? And when this is an equality, this is called 100% polarized light. So as a simple example, if you have Q equals I, then there's no vertical polarization. All the intensity comes through a horizontal polarizer, and in that case there would be no circular polarization. It turns out that for the CMB can be polarized by elastic scattering with photons. It's well known that the scattering of light induces polarization. That's why Polaroid sunglasses work the way that they do. They are such that if you look 90 degrees away from the sun in the sky, you will notice that the light there is strongly polarized. If you've never tried it before, take your Polaroid sunglasses, look away from the sun, and just turn your head as you rotate the linear polarizers, and you will be amazed at how the intensity of the sky changes. Light scattered by 90 degrees through Thomson scattering or elastic dipole scattering is 100% polarized, linearly polarized. So circular polarization is not created by scattering of electrons, at least without a magnetic field. And so the CMB can be linearly polarized by scattering with electrons. But if you scatter too much, then the polarization gets washed out. It gets erased. Any photon polarization you generate by a given scattering, when you scatter through many different random directions, gets geometrically averaged out. So in the early universe, when the scattering was copious, was rapid, there's no net polarization. In the late universe today, after recombination, where the photons have scattered a little bit off of electrons, there is a small residual polarization, and that is sought after in the CMB experiments. So that's all I'm going to say about polarization to prepare you a little bit for later lectures that discuss CMB and CMB polarization. They will deal with these Stokes parameters, Q and U, and the intensity. And I just want to deal with the sum of intensities through cross polarizers, which I will call the total phase space density. So if you like, summing over the helicity states, yes?
So if we want to calculate number density, do we just sandwich this F in between the polar vector, or whatever that's called? Like whatever vector is for the polarization of the
detector.
Sum over
Yeah.
different polarizations? Is that how? Yeah. How do we use this to calculate number densities?
So I'm going to show you that right now. And I'm just going to sum over the polarizations. What I have told you is how to calculate the reduction of intensity when you have a Q and a U that are non-zero. So let me show you the total number density, and then maybe we can come back to your question. So I'm just going to take the trace that assumes that I'm not putting in cross polarizers, or equivalently, I'm not measuring the polarization. I'm just measuring every photon that hits my detector. Charge coupled devices are insensitive to polarization, so they will measure all the polarizations of photons going in. If you put a Polaroid material which has polymers, long chain molecules, where the electrons preferentially vibrate when a light wave goes through along one direction, then only a certain fraction of the light will go through. 1/2 of 1 plus Q over I, or 1/2 of 1 minus Q over I would be the fractions for linearly polarized light with these orientations of the polarizers. And there are simple rules for how Q and U rotate, as you can imagine, when you change the angle. I've shown you 45 degrees and 90 degrees here, but there are simple trigonometric relations which tell you how much intensity gets passed if you have a polarizer at some arbitrary angle. You can find those in optics books. I won't do it. Really, the only important cases are these cross-linear polarizers, which are used in CMB experiments for measuring CMB polarization, or measurements of the total photon number, which sums over the polarizations, or in terms of particle photon helicities, sums over the helicities. So, of course, it's twice the number for a single polarization state or a single helicity. That's why the G factor for photons is 2. Okay. Are there other questions on this stuff here? This is kind of important for later in the lecture series. All right. So now I'm going to return to this expression for the Planck law. If you take the expression that I had for and you write this amount of energy as the energy, which for photons is the momentum P, times F gamma for photons, times, I want the energy contained in a little volume with photons in a given range of momentum. That's d3p d3x. I have to relate momentum to frequency. So in case you want to keep track of units, in SI units or CGS units, put in the C. And E is 2 pi h bar times the frequency divided by C. So we put in those factors. This d3p is p squared dp d solid angle, d omega, so giving the direction of the photon momentum. This is the same, or the same up to 180-degree reflection as the direction in which the telescope is pointed. So the solid angle element here is the same. And I mentioned that, that reflection of directions because you have to be a little bit careful in the CMB literature. Sometimes people will use a unit vector to describe the direction that the photon is traveling. Others will say that the photon travels in minus that direction because they take the unit vector to point out from the telescope. It doesn't matter for the solid angle. So you can cancel the d nus and the d omegas, and for the d3x, that's just dt dA times c. So you end up with, when all is said and done, the Planck law, b nu, is 4 pi h bar nu cubed over e to the 2 pi h bar nu over t minus 1. And I've set the Boltzmann constant to 0. I've kept in the Planck constant just kind of to remind you that this frequency is not the symbol for a neutrino, but the Planck constant is there because of nu being the frequency, astronomers' choice of working with frequencies. The number density, actually let me do this on the next board, evaluate the number densities. That 4 pi is 2 pi h bar, Planck's constant little h, times 2. The 2 is for the number of helicity states, or polarization states. So the photon number, summed over helicities, remember, B nu is proportional to energy. And by the way, the reason why astronomers measure brightness in energy units is because, at least prior to the CCD, a lot of astronomical measuring devices measured the incident energy, not the incident number of photons. In particular, radio receivers don't count photons. They measure energy flux. So that's why the astronomers use an intensity that is energy per unit time, area, solid angle, and frequency. So this is just the number. And you can put in the exponentials, do some changes of variables, and write this as 2 divided by pi squared times our Riemann zeta function of 3 times t cubed, where the Riemann zeta function comes from these Bose-Einstein integrals. Like that. And T really means Boltzmann's constant times temperature divided by h bar c, I think. It's much easier when you set h bar and c equals to 1, as you know, until you actually have to calculate numbers for the experimentalist. Then you have to check all your units carefully. And this zeta of 3 works out to be 1.202. That's a very well-known factor. And then for the the energy density, that's just the integral b nu, d omega. That's 4 zeta of 4 divided by pi squared times t to the 4th. And zeta of 4 is pi to the 4th divided by 90, which I suspect you have probably seen in a StatMech course before. N is 4 is 2 times the number of spin states, the spin degeneracy. Now, that's the energy density of photons. Remembered we showed that for adiabatic expansion, the energy density goes like A expansion factor to the minus 4. And therefore, the photon temperature of the CMB goes like A to the minus 4. And this is where this business of the large heat capacity of the CMB is important, because even if the electrons, if there are free electrons which want to scatter the CMB and change the temperature, because electrons typically will have a different temperature than the CMB, unless they've had time to equilibrate, you really can't change the temperature very much at all from this law below an MeV. So we can say that it's 2.725 Kelvin times a factor 1 plus Z, which is 1 over A. Okay. And that's really very handy, because just knowing the temperature today and that scaling with redshift, we can relate redshift to the CMB temperature. And we can relate the expansion factor, therefore, to the CMB temperature. And so there's a relation that cosmologists use between temperature, expansion factor, and redshift, and they will use them interchangeably to describe cosmic time. So now I have a little homework problem that follows from all of this. An extra one. Using TCMB equals 2.725 Kelvin today, check that result for N gamma being 411 per cubic centimeter, and calculate the ratio of rho matter today divided by rho photons today. It's some numeric prefactor times little m omega little h squared. You remember the definition of omega. Little h is h naught divided by 100 kilometers per second per megaparsec. Okay. So that's quite useful, this ratio, this number, for two reasons. One is that the ratio changes with time. I've asked you to evaluate it today. You can turn that into the redshift at which the photon energy density equals the rest mass energy density of the matter, and that's when the universe, close to when the universe undergoes this matter radiation equality transition. The neutrinos actually contribute as well to the energy density, so it's a slight change from that. The second is that the CMB power spectrum actually measures this ratio quite accurately. And so therefore you can see that the direct CMB spectrum fitting measures the product omega mh squared. And for that reason, people sometimes will write this combination as a little omega subscript m. Okay, I just want to finish up with one very last thing before the break. Well, I can actually do it on this board. No, I will do it here in this portion. I've derived the results for Bose-Einstein distributions for the number density and for the energy density of relativistic gases. For a relativistic Fermi gas, with mu equals 0 and some T, of course much greater than m, in kinetic equilibrium, the energy density is 7/8 times the same formula as for a bosonic gas. So it's pi squared over 30 times g sub x times t to the fourth. And this factor 7/8 just comes from the Fermi-Dirac integral replacing the Bose-Einstein function in this zeta function. Turns out if you make this a plus 1, there's an algebraic relation between the zeta functions that will give this factor of 7/8. And so it allows to write in general that the energy density is the sum over species of G for the relativistic bosons plus 7/8 times G for the relativistic fermions times pi squared over 30 t to the fourth if they have a common temperature. So electron-photon scattering, for example, can establish a common temperature in the early universe if they're relativistic and if mu is 0. But they may not be relativistic, all the species, even if they are in kinetic equilibrium, and they may not all have mu equals 0. So in general, we write this as some G star times pi squared over 30 t to the fourth, where this G star just counts the number of relativistic degrees of freedom with a factor 7/8 for fermions. And if you have a chemical potential, then of course you have to apply a correction to this G star as well. This is very important for cosmology because the universe is often quite close to kinetic equilibrium. Really, the photons always have a distribution very close to kinetic equilibrium. So you can always describe the universe by temperature T. And then to work out the cosmic expansion history, all you need to know is G star as a function of T. And that will allow you to integrate the Friedmann equation. So that's where I'm going to stop for today. We have a coffee break. I'll be happy to take questions probably during the coffee break, because I don't want to cut into it now. And come to the transit observations this afternoon.